this episode of Remote Linear Algebra, we'll be talking about what it means for a matrix to be diagonalizable. Here we have a 3x3 matrix, and it is diagonalizable. Not all matrices are diagonalizable, but this one is. It means that its eigenvalues can form a matrix which we will call D. The order that we put the eigenvalues doesn't matter, but once we've decided which eigenvalue goes in which column, another matrix, which we'll refer to as P, has to be set up in a certain way. The eigenvalues for this particular 3x3 matrix are 8, and then the irrational number -2 plus 2 times the square root of 5, and then its conjugate, -2 minus 2 times the square root of 5. So notice each eigenvalue is in a column with the other entries equal to 0. And so I've put 8 in the first column and then the other 2 eigenvalues in the other columns. Now, if a matrix is diagonalizable, which this one is, then D works in concert with another matrix, which at the moment we're calling P, so that P times D, the diagonal matrix, times P inverse gives you back your original matrix. Now let's talk about how to get P, because we've already talked about how to get D. If you build a new 3x3 matrix off of the original one and each eigenvalue, so for example, 8 was one of our eigenvalues. So in this column, I have -6 minus 8, and then I've left these other entries as they were. And then in the second row, I have 2, and then 2 minus 8, and then I've left this alone. And then the third row, I have 0, 0, and then 8 minus 8. So notice down the diagonal, I took the original matrix and I subtracted the eigenvalue 8, leaving all the other entries as is. If I RREF, or completely reduce that with row echelon steps, I get this matrix. Now, this matrix is the same one that was used to come up with a characteristic equation for this 3x3 matrix. And it gives you sort of the solutions to that system of equations in which you knew that you wanted this matrix times a vector to equal a constant multiple of that same vector. So this should be the x, y, and z set equal to 0 for a system of equations. If I run down the first row, then that reads as x minus 0.1z equals 0, and then the second row is 1 minus 0.2z equals 0, and then the third row is just all zeros. That gives us a general basis vector of 0.1, 0.21. That means that x is always 0.1 times whatever z is, y is equal to 0.2 times whatever z is, and any vector that fits that form will be an eigenvector for the eigenvalue 8 and this original 3x3 matrix. So this is the eigenbasis vector for 8. Then we can do the same thing for the other 2 eigenvalues. They're just a little messier than 8, but you do the same thing. Down the diagonal, you take the original values from the matrix and you subtract the eigenvalue. You leave the other entries as they were from the original matrix. You find the row reduced echelon form. For -2 plus 2 times the square root of 5, you get this matrix, and that reads as x minus 0.236, you know, that messy decimal, plus 0z equals 0. So that means that x is always that 0.23 decimal times y. And then this row tells you that z has to always be 0. It says 1 times z, and remember, these are the coefficients of x y, and z set equal to 0. So the eigenbasis vector for this eigenvalue is 0.23606, you know, that messy decimal, 1 for y, and then 0 for z. So any vector that's of the form where x is 0.23, you know, that again, you'd want to carry out that decimal as far as you could, times y, it will be an eigenvector for this eigenvalue. And then doing the same thing for the third eigenvalue. The third eigenvalue was the conjugate, -2 minus 2 times the square root of 5. So again, down the diagonal, you alter the diagonal by subtracting the eigenvalue. You leave these other values as is, and then you do the row reduced form, and you get this matrix. And that matrix reads as x plus 4.23 messy decimal times y equals 0, and then once again z has to be 0. So the eigenbasis vector for this eigenvalue is -4.236, because if you move this to the other side of the equal sign, you'll get a negative, and then 1 times y, and then 0 for z. That gives us a p where this is the eigenbasis vector for 8, this is the eigenbasis vector for -2 plus 2 times the square root of 5, and this is the eigenbasis vector for -2 minus 2 times the square root of 5. If I then take that matrix times D times the inverse of this matrix, I will get back my original A. And by the way, if you do the reverse engineered version, if you do the inverse of P times A times P, you will get your diagonal matrix. Now, why would we want to do this? Well, it turns out that if you are going to do some operations, like raising to a power is an example operation, that this would be true. If you take a diagonal matrix and you raise it to a power, it's very easy. Just the diagonal values need to be raised to that power. If you actually tried to work through raising this to the 4th power, and you took 4 of these and multiplied them together and did all of the matrix multiplication, it's messy. It's messy for a computer to do too. Like it's quicker and easier for a computer to be programmed to do this than to do this. So it also makes calculating a to the 4th easier by using our definition of how A is related to D. If I took P and I multiplied it by D to the 4th, and then multiplied it by P inverse, I will get A to the 4th. And overall, this would take fewer steps than if I actually took this matrix and did the matrix multiplication. So that's just an example of why you might want to take a matrix and use its diagonal form. There are some processes which end up taking up fewer steps and are cleaner. Showing this on the calculator, just so that you believe me, we have in, I think in B, I put this is P, okay? So you notice that 0.1, 0.21, and then this is the eigenvector, or the eigenbasis vector for that second eigenvalue, and then if I go over, here's the eigenbasis vector for the third eigenvalue. So B is P, and then in the calculator C, I put this is the D. So notice it's 800, and then 2.47 is what -2 plus 2 times the square root of 5 is. And then this column has negative 2 minus 2 times the square root of 5. So if I take B, which is my P, and I multiply by C, which is my D, and then I multiply by B inverse, notice I get negative 6, 2, 1, 2, 2, 1, and then 0, 0, 8. So I get my original matrix. That's my matrix A. I also could take A and raise it to the 4th power. And you could see that you end up getting, I'll bring the calculator back in a second, but you end up getting 1,664, negative 384, 320, negative 334, 128, 832, 00, 4,096. So again, that's what I have here on the calculator. Then if I take P and then I raise this to the 4th power, and then I take this matrix, I truncated the decimals, but you really should use the full decimal. Take the inverse of P, we should get A to the 4th power. So doing that on my calculator, remember C had the diagonal matrix. So if I go into the calculator and I take B and I multiply by C raised to the 4th power, and then I multiply by B inverse, I get that same matrix that we said was A to the 4th. So that's just an example of what we've been talking about actually in practice.